our next speaker is JP Swinski, who will be talking about H5Coro, the HDF5 cloud optimized read-only library. So JP, please.
Hello, everybody. Okay, so yeah, I'm JP. Let me share my screen here. Okay. So my name is JP. I work for NASA. I'm a software developer at a Goddard Space Flight Center, which is an Earth science facility for NASA just outside of DC. And I'm going to be talking about H5Coro, something that we've developed over the past 6 to 8 months. So before I get into it, though, just want to pose this question for everybody. Just consider this. So in the project that I'm supporting, that I'm working on, we have science data product services that are running in AWS that access H5 data that's stored in S3. We have also on the same project Python scripts that are not written by software developers, but by researchers, scientists that read H5 files locally, just from the local file system. And then we have Fortran programs that run on supercomputers that also generate H5 products for us. And in all three of these cases on our project, they all use the same underlying HDF5 library. Even though the environments that they're in are very different, that the use cases, everything about these applications are different, they're still using the same H5 library. And so historically, how do you get them to run optimally? Well, you tune the library, you tune the environment, you tune the application, you use things a little bit differently, there's a lot of work that has gone into how to tune the HDF5 library for different environments. But for us, when we moved to the cloud on our project, we're in AWS using EC2 and S3. We really ran up to an obstacle that we couldn't get past. Tuning was not enough. And I think a lot of people are facing the same challenges. And we see this because when I've talked to other people, there's kind of this set of different approaches people are taking to solve this problem. They're looking at restructuring the H5 data inside, rechunking. This is something that we tried. They're looking at, there's efforts that are building these optimized indexes that overlay the data. There's a couple efforts that are doing that. And then there's groups that are looking at just reformatting the data entirely when they move to the cloud. Now, I think all of these are good approaches, and certainly we, in our future on the project, we may pursue some of these as well. But for today, and what I'd like to talk to you about today is adding a fourth option to the mix. And that is, instead of changing the data, what if we thought about changing the library? And so just think about this for a second. So because there is, in practice, for all practical purposes, there's only one implementation of the HDF5 format. That's the HDF5 library. And because there's this one implementation of it, really the library becomes the standard. So the characteristics of the library, the software implementation, become the characteristics of the H5 format specification. Similarly, the limitations of the library become the limitations of the format. So I'll hear people saying, and a year ago, even I said, well, H5 is not well suited for the cloud. And I hear this a lot, where I work. Well, H5 is not well suited for cloud environments. And I was like, well, that's actually not the case. It's really right now the HDF5 library is not well suited for the cloud. It wasn't written for the cloud. That wasn't its original design target. But because there's just this one implementation that is kind of the de facto standard, those two get intermixed and combined together. So what we decided to do was what if we change the library? And that's what H5Coro is. It is an attempt. So on our project is ISAT2 slide rule. So ISAT2 is the mission out of NASA. Slide rule is the software project. We developed an alternative library for accessing H5 data specifically stored in the cloud. So what is it? Specifically, it is a C++ module inside our slide rule server that was written from scratch. And the goal is that to implement a performant HDF5 reader for H5 files that reside in S3. It does read files that are local in the local file system, but the goal is S3. That's its design target. What is our data model on our project? Our data model is all of our data is static. So the data that we're reading was written once and is never updated. It's a science data product. And so we read it many times after that. Secondly, our data is time series. So the data as it is stored in the chunks in physical memory are stored sequentially in the chunks. And then our environment is S3. And so we have very high latency, which is bad, but also very high throughput, which is good. So given these things, right, so how would we do this? Well, because of these characteristics, the library strives to minimize the number of IO operations as much as possible. So even if we have to read more data, our main goal, because of the high latency of S3, is we don't want to issue an IO operation unless we absolutely have to. And so we do that through two main things. We do that through different caching techniques and through heuristics that try to build intelligent range gets to S3. Just to give you a little bit of background before we go into the details, and I actually want to get through to the later parts of these slides. So I'm going to go through this a little bit quicker so I can slow down at the end. So slide rule is a server-side framework. It's implemented in C++ and Lua. And the main thing it does is it provides a bunch of REST APIs for processing science data on demand. So researchers can hit our system with a science processing request. We take lower level data products, and using the parameters that they supply at the time of the request, we pull the data from S3, process it into higher level data products, and return it to the user in real time. So it's trying to change the model from an archive-based science distribution system to really a science data as a service. And this effort's a collaboration between the University of Washington and Goddard, and it's funded by the ISAT2 program. The two main goals that are pertinent to data are the first two, which is we need to be very cost effective. Practically speaking, that means that we've got to scale dynamically. So we've got to have near zero costs when we're not in use, and also then scale when we're needed. And we also need responsive results. So both of these, how we manage the data plays into both of those goals. This is what our system looks like. We've got slide rules, the heart of the system. We're hit by, right now, mostly Python clients that do requests. And then we spin up a bunch of servers, process the requests, and we're accessing the data. Historically, we were accessing it through HSDS, which was pulling the data from S3 for us. This is a blow-up, zoom-in look. Our application links in the HDF5 library. It uses the REST vol connector, and that's what talks to HSDS and the service and data nodes that go out and hit a metadata repository and the H5 files that are all stored in S3. So what are the limitations of that approach that I just described, and the reason why we needed to do something? Well, there are certain obstacles that were really preventing us from having a cost-effective system and a responsive system using the HDF5 library. The first was that all of the calls are serialized in the library. So even if you have a very parallel system that's able to be very highly parallelized, once you go into the HDF5 library, they're all serialized for you. Second is that the HSDS was issuing multiple HTTP requests per dataset chunk. So our system became very chunk size dependent. If we wanted a little bit of data, that's okay. If we wanted a lot of data and there was little chunks, well, then that became a problem because we were issuing thousands and thousands of HTTP requests to S3 just to read a little bit of the data in the file. And then lastly, there was a requirement to maintain a metadata repository, and that posed some logistical as well as cost problems. So I'm going to skip over some of these things and just to go through a little bit at the end. So this goes into more detail about the serialization and the chunk size dependency. And I'm going to jump down here to HDF, the H5Coro and what we've done there. So what we did is we replaced the HSDS and its connection with HDF5 and REST file, and we moved it into this one module. And so what that system now looks like is instead of having this stack, we now have just a module that goes directly to the H5 files. And notice there's no line to the metadata repository. So the module goes directly to the files stored in S3. And the four things that really benefited us using H5Coro is one, all the reads are concurrent. So it was written from the beginning to be highly parallelized. So you can thread it, you can build, we can even look into using async IO if we needed to. All of the range gets, all of the gets to S3 are range gets, and they use a heuristic to determine the optimal start and stop range to read. It tries to guess where the beginning and the end of the data is in memory using the way it's laid out in the file, and then tries to read that with one read. And if it doesn't succeed, it'll then use a couple other reads to get the edges. The system is serverless, so everything scales naturally with the application, and we don't need a metadata repository. Instead, we use caching to get our performance gains. So this made a huge advantage for us when we switched. Just looking at doing some test runs in the initial system, our performance test was taking about 2.5 hours, and using H5Coro, it takes 2 minutes. And that sounds crazy, but it really was a function of the fact that the HDF5 library was never written to be highly parallelized in a high latency environment. And so just by taking that into account, tremendous performance gains. And in our actual system with a typical workflow, our typical workflows went from about 1.5 hours down to about 25 seconds. So you saw the test case before, and then for typical use cases, it is a similar performance improvement. But this is what I want to spend the last couple minutes of the talk on, is this API here. So this is the entire API that we use into H5Coro. So there's a read call, you give it a URL, which is the fully qualified path to your file. You've got S3:my_bucket/folder/subfolder/my file, whatever. So you got your URL, you got your data set name, local/heights. You have a value type, which we use. There's a dynamic value type, which means just use the one in the file. We have which column for multi-dimensional data sets, a start row, a number of rows to reads, and then a context structure that provides a pointer for caching. And the interesting thing here that I want to pause on is to say that we had this big system that was actually able to support reading all of our data. And when we looked at it, we were able to boil our entire access to H5 down to this one API call. Now, it may be true for you guys that this API call doesn't work for you. Maybe it's a different one, but the challenge that I want to pose is, could you look at your system and say, is there a single API call that I could boil my entire system down to? And once you have that one API call, that's your interface to the data. And if you can then look at that interface and start reasoning about it, how would you write the underneath library to take advantage of it, right? So I can see right away that every data set read is atomic. It's exclusive of any other one. So I can parallelize on data set reads tremendously. I know that because I'm time series, I collapse any higher level dimensions just with after the first one. I can take advantage of the data being next to each other and what that means for doing intelligent range gets. Again, I know my time is up, but that is really what we did. We said, if this is our only interface to our data, what would the library underneath look like to optimize reading the data? Okay, so that is all my time. I'm going to stop sharing and open it up for questions.
Thank you, GP. Actually, but just a reminder to speakers, you can spill into the question area, just a question time. It means simply less time for questions. So
okay, well, if there's not many questions, then I may throw a couple more points in there.
Right. Mm-hmm.
So I have a quick question. Are you thinking of supporting any protocols other than S3?
The library, it is written so that we abstract all of the IO into a driver. And so, yes, but it'll really be an as needed basis. So for the two that we need is just local file access and S3. But the library, if you generalize it and say the library is meant to minimize the number of reads at the expense of overreading the data, if that fits to the environment, then H5Coro would be a good fit. If for some reason there was a system that had very low latency, but low throughput, then H5Coro would be a horrible fit because it's going to overread the data.
There is a question in the chat from Rafael Girardo.
Oh, did you completely rewrite the H5 Data Access API? We actually rewrote from the ground up, so there's no linkage to HDF5 lib at all. We just took the spec and we wrote to the spec. And that's one of the things that I noticed. The spec is large and we were not able to implement the entire spec. But for one, we didn't implement any writing. So it was only reading that we implemented. And that was a huge saver. And also we never have to worry about something changing after we read it the first time. It'll be in the same place, the same value the next time, because just right. And now that's not always true for all uses of HDF5, but for our use, it was. And for a lot of science data, right? It's a science data product. It was developed, output by some supercomputer, 3 years ago, and it's going to be the same forever. And if it changes, it's a new version of the data product. So that fit for us.
Andy, please go ahead. You had a question.
Yeah, just a naive question is I mean, you don't seem to support reading metadata, attributes and things like that. So don't you have any, or what is the story? Do you have them stored in some other database? Or?
So right now, we don't support reading attributes. That may change. All of the data on our project is stored in data sets. So even things like if we need to look at spacecraft velocity or spacecraft orientation, that is a small data set. They don't store science data in the metadata. The only things that our project stores in the metadata are human readable things. And so for a service that's just chunking science data, we didn't need it. It's not hard to add that, and that's something that's on our to-do list.
There is Mark Headley wanted to ask the question. Mark, go ahead.
Lovely, thank you very much. Thanks for the presentation. My question is, do you have links between different variables? Do you have a variable in your data which then has a reference to another variable that might contain associated metadata that you've tried to support?
So if I'm understanding correctly, the H5 spec supports symbolic links. Is that correct?
Yes.
Yeah, so we do not support that. Not that it, again, there's some charts at the end. I don't know if everyone has access to the charts. I built there's a whole table where everything in the spec is documented, what's supported and not. And really, it's just going to be time for us to eat away at that and add more and more. The only thing I would like to point out, though, is as I was going through the spec, it seemed to me that there were a lot of features that were added to the library in order to support small use cases. And that over time, there was a tremendous growth in the size of the spec because of that. And I think that there may be some benefit to having a subset of the spec, because if you just use default settings and just write an H5 file, like we found in a lot of projects, it's actually a narrow use. There's like a very narrow use, and you get like 90% of the data that I've seen is just really narrow use. Maybe going back to that would help other people kind of write these libraries, which don't take a ton of time if there's a small spec, and can really optimize for a given environment. And they're using H5, and now you get all the benefits of having all of that tooling and infrastructure that H5 brings with it. So anyway, just food for thought.
Yeah, thank you very much.
Yeah, it's really interesting.
Time for another talk. JP, there are some questions for you in the chat window if you answer.
Okay.
Thank you. Thank you very much.